Good morning, and thanks to all of you for being here. It's nice to see a few familiar faces. I've been here before, and then so many new ones, so thank you for coming. And thank you for that wonderful introduction. I think Jimmy knows more about me than I know about myself, so I really enjoyed that. So as he said, when I started at UBC about 14 years ago now, I was coming from a background in mesoscopics and making little gate-defined structures on gallium arsenide 2 eggs, and I did a little bit of that work in my first few years at UBC. And then, since then, I've sort of moved away from that into other areas. I work in 2D materials and some fractional quantum Hall and some other things. But then, just in the last few years, we started coming back a little bit, and this experiment that I'll tell you today about is really back to those early mesoscopic roots of mine. But I like it because it's an experiment that combines a lot of branches of physics, actually. Actually, in a way, it combines many branches of physics, but at a very simple level. So these are all sides of physics that you probably learned about in undergrad, or if you are an undergrad, then you're learning about now. It combines thermodynamics at a quite basic level, thermodynamics and specifically entropy. There's really first-year level quantum mechanics in terms of spin 1/2 systems and what are the degeneracies of 1 or 2 or 3 spins together. Just again, at the most abstract, simple level, leaving aside all of the complexities that normally come along with condensed matter physics. And then there is, of course, the structure that we have to begin with, which is one of these, very advanced 2D electron gases built in gallium arsenide that by now is, the substrate that people use for spin qubits and all of this kind of thing. So it's an experiment that combines lots of different fields, hopefully in a way that will remind each of you in the audience of things you've seen before, and now you can see it really coming to life in what I think is a very pretty experiment. So I'll show you how we'll measure the entropy of single spins. Let me show you basically the entire experiment encapsulated into this picture. So we're going to trap single electron spins in this little structure here. So this picture is an SEM micrograph of the surface of a gallium arsenide wafer. There's a 2D electron gas that lives everywhere in the surface, in the plane of the screen. And these lighter colored regions are metal gates on the top. Scale bar is missing from this picture, but the width of this dot is about, or the dimension across it is a few hundred nanometers. So of course, if you actually think about how many electrons are in this little region of gallium arsenide, there's zillions, right? It's probably 100,000 gallium or arsenic atoms on the side. There's a lot of electrons in there. But in terms of the number of conduction electrons that are living in this 2D electron gas, we can tune the voltages on these gates to confine just a single electron in there. And of course, we know that a single electron will have spin 1/2. And so the idea of this experiment is we're going to try to measure the entropy of an electron living right in there. So entropy, of course, is a thermodynamic measurement. In order for that to have any meaning, we have to be able to look at temperature. And so we use this piece on the other side as a heater. So we can inject current, at some relatively high voltage relative to the rest of the problem into this region in the middle. We blast it with hot electrons, and we create a hotter Fermi sea in here. And we look at the thermodynamic response of this single electron, and from that, we deduce its entropy. And so that sort of is this talk in 2 minutes. We're going to be looking at the entropy of an electron trapped in here by looking at its response to temperature that's affected through here. Okay, so before I begin, let me tell you about the team that did this experiment. So it was really led by this gentleman here, Nick Hartman. So he was a postdoc with me. He's actually just now left to start as a staff scientist with Microsoft in Purdue, doing their quantum computing effort. It was begun actually almost 10 years ago by a PhD student, former PhD student, Mohammed. So I'll tell you a little bit about Mohammed's work in the middle of the talk. And then it was also Christian, another PhD student, helped with it, and Sylvia, who is also my wife, as a research associate in the group, and she helps with everything, including getting this experiment to run much better. So this was the experimental team that was responsible for the measurements, again, really led by Nick. The wafers are crucial to these efforts, and those were grown by Mike Manfra at Purdue and his, I guess at that time, postdoc, Jeff Gardner, and now a staff scientist, and his PhD student, Saeed. So these are the people that were really responsible for this experiment. And I realized as I was putting this talk together just a few minutes before you all showed up that I left a very important name off the bottom. So now that Nick is gone, the experiment was headless. So now it's being led by a brand new PhD student of mine, Tim Child, whose picture I do not yet have. But anyway, if I'm back here in a few years to tell you about the progress, then it'll be led by Tim Child. Okay, so let me take a step back and talk about entropy. Of course, I'm sure all of you have learned about entropy in a thermal class, and you've probably seen entropy measurements as ways of exploring exciting new condensed matter systems, new crystals or magnets or something like this. Very often you measure heat capacity or something connected with entropy as a way of understanding really what is the underlying nature of the electronic state. What are the degeneracies? What kind of hidden orders are there? Is there something interesting from topology, frustration? These are all things that you can figure out by measuring entropy. But as an experimentalist, you almost never measure entropy by itself. What you measure is something else. And for bulk system, it is almost always heat capacity. It's a very powerful tool. Let me give you an example. So this is a paper from a few years ago looking at a material, dysprosium titanate. And here you can see a picture of the crystal structure. It involves a bunch of tetragons with spins at the corners. And you end up with frustration in this spin system that is directly analogous to the frustration that oxygen and hydrogen atoms feel as they try to make water ice. So some of you may know that ice is a fascinating crystal structure. It's actually quite hard to understand. And one of the reasons is the frustration that's built into the crystal structure. The lengths of these different bonds just don't come together to make a nice, simple ground state for ice. And as a result, you have all of these degeneracies in ice that give you interesting heat capacity effects, for example. And so this was a way of seeing, essentially, the thermodynamics that go into water ice in a spin system. It ends up being much more controllable in a spin system. And so they were able to see, by measuring the entropy of this spin ice system, again, really what they measure is the heat capacity. It's typically plotted as 1 over temperature for reasons you can understand if you go back to first year thermo. So you measure heat capacity, and from that you integrate and you extract an entropy. And by looking at the absolute value of this entropy, they were able to see basically what is the nature of the spin ground state of this system. And they were able to see the frustration that's built into the spin system by a suppression of this entropy below this blue line, what you get just for free spins, down to here. Okay, and so this is an example of an entropy measurement used to see what something that is, in general, exciting for condensed matter systems, looking at frustrated spins. Of course, by now there's all kinds of new directions that this kind of work is going. But I want to show you this just as an example of the kind of thing that people often look at it for in bulk entropy measurements when they're looking at exotic new condensed matter systems. Okay. I seem to have a problem with the bottom of my slides, but let's see. Okay, so how about if we don't have a bulk crystal to work with? Okay, and so instead of the natural unit of entropy being the ideal gas constant, R, which is an amount of entropy per mole, essentially. We don't have a mole of atoms around, we just have a few particles. And then the natural unit of entropy is the Boltzmann constant. 10 to the 23 smaller than this. How would we measure the entropy of such a system? Calorimetry won't work. Okay? You would have to find a thermometer that itself is, has heat capacity of the same order, and that just doesn't exist. Okay, so how would you set about measuring entropy of just a few particles? Well, first, why? Why would you want to go about such a difficult task? I think for us, the motivation was that there's a lot of examples of electronic states with either strong interactions, non-trivial band structure topology that can host exotic particles or quasiparticles. Not bosons, not fermions, anyons, non-Abelian particles. There's all these kind of new exotic emergent particles that appear in condensed matter systems when you combine when you bring new elements into the Hamiltonian. And recently, it's become possible to engineer and control these states at a single particle level, which is very exciting both for understanding them better. If you can really control them piece by piece, if you can build the Hamiltonian one element at a time, it's much easier to understand what you have than if you just have to grow a crystal and figure out what's inside. And also, when you try to look at using these quasi-particles in some way, for example, for quantum computing, what you can do with topologically exotic particles, then it's important that you can control them one piece at a time, one particle at a time. Okay, and so these are some motivations to be able to look at entropy not of an entire crystal, but just of one or two particles. But again, heat capacity is impossible to measure for such a particle, or for such a system. It's just too small. And so you have to find another way to do it. Okay, so since I've brought up now the challenge, how would you measure the entropy of a single particle? Let me make an analogy to measuring magnetic moments. Okay, people have been doing magnetometry on crystals for a very long time. But a decade or two ago, as people started trying to make spin qubits, then it was important to be able to measure not just the magnetic moment of a chunk of something sitting on the table, but actually the magnetic moment of a single electron spin. Okay, and so how would you measure the magnetic moment of something as small as h bar? And of course, over the last few decades, there have been a few different approaches that work for this. But one of the first that worked effectively for measuring such a tiny magnetic moment in a solid state structure was by using a device like this. So let me tell you about what you have here. This is again an SEM micrograph. Even though the gates look very similar, this was actually built in a different group, Elzerman et al., about 15 years ago. And so again, there's a spin confined just in this little circle here. And by performing a sequence of gate pulses, of voltage pulses on these different gates, they were able to perform an operation such that if the spin was up, it would leave, and if the spin was down, it would stay, or vice versa. Okay, and so depending on the direction of the spin, you could change whether the charge in here was 0 or 1, or 10 or 11, or something like that. Okay, you could change Q in this dot as a readout for the magnetic moment of this spin. And so this was the first approach for measuring single spin, or one of the first approaches for measuring single spin magnetic moments. And it went by the name spin-to-charge conversion. Do you have a question?
Yeah, I mean, that's lovely, but it's not exactly measuring an angle of 11 or ratio.
It's not measuring. It's true. It's not measuring. It's measuring the projection of that spin onto the z-axis or something like that. It's not measuring the quantity h bar.
Yeah,
That's true. That's fine. Yes, that's fine.
Yeah. Okay.
So I'm going to show you an experiment which will measure something similar, which is an entropy divided by KB. So in that sense, what we're measuring is sort of the same, except, and I'll show you that we have a very high level of accuracy for that ratio. We can also measure Boltzmann constant, if you like, with maybe a 10 or 20% accuracy. But, all right. But I'm Canadian, so.
You've agreed to it too.
All right.
I'm joking about the fact that the new SI.
Okay, I see. Good. So it's one, then. No, I understand. Yes. Okay. So this. Okay. So let me take a step back. I want you to have this in your mind, basically, as the approach we're going to take for measuring entropy of just a few particles. We're going to convert them to charge, and by that, measure the entropy. But now let me tell you really where this experiment started. Let's say what our motivation as a group for measuring entropy. And that was to try to measure a fractional quantum Hall state. So this is a state that forms from a sea of 2D electrons at very low temperature in a very high magnetic field. There were papers out there suggesting that at a certain magnetic field, then these electrons reform into non-Abelian quasiparticles, so a new quantum Hall state whose excitations are not like fermions or bosons, but a completely new kind of particle. And we were interested to measure whether this was true or not, following a proposal by Addie Stern and Nigel Cooper to do it by measuring their entropy. Okay, and so this was the origin of our efforts to measure the entropy of just a few particles. So let me give you just a little bit of background into that experiment. So here I'm showing you schematically electrons in a Fermi sea. So I'm not sure you can see this dark blue background, but this is the Fermi sea filled up to some Fermi energy, and the electrons are blue in here. There's 9 or 10 of them, but of course, in reality, there's a lot. And this is at zero magnetic field, and they're all free to bump around in this Fermi sea. And then you turn on a large perpendicular magnetic field, and quantum mechanically, the state or the system reforms into massively degenerate Landau levels. And so these white lines are the Landau levels, and they're separated by the cyclotron energy. And so if you're filled up to some Fermi level, actually I wish that were down here, then you would have these two Landau levels completely filled. Again, they're massively degenerate. And this next one completely unfilled. So this particular state would correspond to the second Landau level because there's two Landau levels that are completely filled. If you lower the magnetic field slightly from this point, you reduce the degeneracy of each of these levels, and so you end up with two levels that are completely filled and some electrons left over. And if the number of electrons left over is such that this third Landau level is half filled, then in a way, these electrons feel the same way this 2D electron gas would feel if you went to a much higher magnetic field where each electron was coupled to two flux quantas. The ratio between flux quanta and electron density was 2 to 1. And in this situation, electrons reform into composite particles. This is a theory going back a few decades. And these composite fermions have some exotic properties, or many exotic properties, one of which is that in this situation, where there's these two filled Landau levels underneath them, apparently they make not only composite fermion particles, but pairs of composite fermions. Okay, so 5/2, this state here, is an inert, two filled Landau levels, and a half-filled Landau level on top. These fermions pair, in theory, to form a p-wave superconductor effectively. And it was this exotic, new, sort of emergent state that we were excited about measuring. The theory was put forward by Moore-Reed that these would be non-Abelian quasiparticles. Because they're non-Abelian, their exchange statistics, they don't get just a phase when they go around each other, but you actually get a new wave function that's orthogonal to the first one. And so as a result, if you think about all the ways of moving electrons in some big Fermi sea around each other, which gives you a new ground state each time, you have a massively degenerate ground state as a result. And so this gives you an enormous entropy. So the degeneracy is 2 to the number of particles in the Fermi sea, which is some astronomical number. And when you take the log of this, you still end up with a very large entropy. And so this state is exciting in the fractional quantum Hall world. And the proposed approach for measuring it was entropy, because that looks directly at the degeneracy of the ground state. So that was this paper. And the approach for doing it was, again, to turn the thing we're interested in, entropy, into something that we're much better at measuring, which is charge, or in this case, a voltage. Okay, and so the proposal was to use this Maxwell relation. The mu dt, so that's chemical potential, temperature, ds/dn, that's entropy with respect to particle number. Okay? And so here's a quantity we want to measure. N and T, we have pretty good handle on as experimentalists, the temperature or the number of particles. And mu, the chemical potential, this is very closely related just to a voltage, which is pretty easy to measure. Okay, and so the idea here was to look at how the voltage oscillates as the temperature changes, essentially, as a way of testing this entropy. So this is an entropy-to-charge conversion. So we worked, okay, sorry. Well, yeah, I'll show you one more slide. So one approach to this is to measure the voltage directly. It turns out in many ways that's hard, but something that you can do much more effectively is to look at just one or two localized states, and to measure chemical potential by the motion of the charging, or by the chemical potential dependence of the charging of these states. So if you imagine a localized state, and you have some Fermi sea filled up to some chemical potential, and you raise the chemical potential, then this localized state will charge one electron at a time. And so monitoring the charging of this state is effectively reading out the chemical potential. And so that was the proposal a few years after that Cooper and Stern paper came out, was to measure this effect by the charging of localized states. And so this specifically was the experiment that we were heading towards. Yes, I'm not sure I would call it a phase diagram, but it is a, yes, exactly. These lines are separating charge states. So in that sense, it is a phase diagram. To here, you have 0 electrons, 1 electron, 2, 3. And down here at low temperature, you can see these lines go slanted left, slanted right, slanted left, slanted right. And that's telling you about the change in entropy between these two states. And so this was the proposal to measure the non-Abelian character of these quasiparticles. We tried this experiment. Mohammed tried this experiment. This was the PhD student I mentioned who started this project. It turns out it's in 2D electron gases that are good enough to see 5/2 fractional quantum Hall, it's very hard to get nice quantum dot physics like this where you can clearly see these charging states. So this experiment did not work. We're still working on it. But what I'm going to tell you about today is what happened when we took a step back and said, okay, maybe we can't measure the entropy of the 5/2 state, but it's a very interesting approach using quantum dot charging diagrams that people have been measuring for 2 decades now as a way of looking at all different kinds of quantum dot physics, but now as a way of looking at entropy. And again, it's all based on this Maxwell relation that relates this voltage axis changing with temperature, so voltage and temperature, to the change in entropy as you add one electron at a time. Okay, so to generalize the approach, and this all came from that paper dedicated towards 5/2, quasiparticle statistics are reflected in the spectra of charging of a local trap in the same way that quantum dot spectra reflect spin and fermionic statistics of electrons. And so it was really this sentence that we set out to map in our experiment. This first part, that was their idea of measuring non-Abelian character of the 5/2 state. And so we wanted to say, okay, well, this part may be too hard for material reasons, but let's see if we can look at the spin and fermionic statistics of just 1 or 2 or 3 electrons in the same way. So what do you need for this? You need to be able to localize a few charged particles. You need to have a situation where entropy depends on the particle number. That's an important ingredient. The simplest realization for this is electrons in a quantum dot, and that's what I'm going to show you today. So with that, let me begin sort of the second half of the talk, which is showing you specifically how we measure the spin entropy of 1 or 2 or 3 electrons in a few electron quantum dot. So I understand from Jimmy that this audience is somehow mixed, condensed matter and atomic MO. So I'm not sure how much review to give here, but I'll give a full review, and those of you who would like to rest can rest. So this picture you've seen already, now colorized to make the background purple. So you can imagine electrons living everywhere here. Here I have nicely gold-colored metal gates on the surface. Again, the scale bar here is a few hundred nanometers across the quantum dot. And we put negative voltages on each of these gates to push the electrons away from underneath them. And so the electrons that are left are all out here in this reservoir or in this little circle where you can see a few little arrows showing, in this case, well, something like a singlet state. Another important ingredient of this experiment is going to be a local charge sensor here. So you can see a constriction that we make between this gate and that gate. Electrons can flow through here. But if we tune this gate voltage so that this is just at the point where electrons have to tunnel across, then the conductance from there to there is very sensitive to the local charge in this quantum dot. Okay, and so by reading out, here we apply a voltage, we measure a current. By measuring the conductance through this little local FET, we can read out the charge on this quantum dot. So that conductance there on this charge sensor, I call G-sense, G for conductance, sense for the sensing element. And so this graph here shows you what that sensor conductance looks like as we pull electrons into this dot by making a more positive gate voltage here in this middle gate. So VP here, That's V on the plunger, voltage on the plunger is the bottom axis. It's like the chemical potential. It maps directly to the chemical potential of these electrons. So you can think of this as us ramping the chemical potential. And this is the readout of the charge sensor. So you see there's some cross-capacitive coupling between that gate and this region here. And so in general, there's an upward slope. That's just telling you that a more positive voltage on this gate opens up this constriction. But also you see these little steps, or these little jumps. Each jump is telling you the arrival of one more electron into this dot. So here we have a big blank region. There's no electrons in this dot. No matter how negative we go, we can't go less than 0 electrons in here. But then when we get here to about minus 350, the first electron jumps in here from the reservoir. And you can, these arrows are showing you the arrival or departure of an electron. Okay, so the electrons jump in one at a time. And so here you see the first electron, second, third, fourth, fifth. Here's how this whole structure looks just in schematic view with energy on the vertical axis and space on the horizontal axis. Here we have the reservoir up there. Here we have the discrete levels in the quantum dot. And you can see there's a chemical potential for the n-1th electron, the nth electron. Each number of electrons has some chemical potential associated with it. And so depending on which chemical potential is above and which is below the Fermi sea, you can figure out how many electrons are in the dot. This picture you're shown that you see here schematically is as the nth electron jumps in. Any questions about this picture? Okay, guess that was too basic. So the signature, it's okay? All right. So the signature of entropy in this experiment is, again, to see the chemical potential shift with a temperature change. Okay? And so we're looking for a shift in this x-axis. We're looking for these charge transitions to shift left or right as we change the temperature. And that the amount of that shift will read out the entropy. Okay, so the charge transitions shift by an amount that depends on the entropy change from n-1 to n electrons. Okay, so now let me show you, let me zoom in to one of these little charge transitions. Okay, and so I think in the next slide I zoom in just to the 0 to 1 electron transition. So it's right, this crossover from there to there. Okay, zoom in on that guy. This is the conductance through that charge sensor. So now my horizontal axis is rescaled. It's still in units of millivolts that I'm applying to the gate, but there's a 0 point defined at the midpoint of this transition. All right? And so this is showing you the arrival of the first electron as it jumps down. The conductance drops as we get an extra minus charge. There's an overall upward slope that's coming just from the cross-capacitance between that gate, VP, and the charge sensor. But you can ignore this overall upward slope. These should, in principle, be horizontal. Okay, so when the temperature increases, there's a few things that are going to happen. First of all, the Fermi sea broadens. And so this charge transition will happen over a larger gate voltage range. Energies are all washed out. But also, if there's an entropy change, we expect this to shift. All right, so now let me show you qualitatively what this will look like as these two things happen. The transition broadens and it shifts. Okay, so let's start with a situation where there's no entropy change. Okay, so an example of that would be if you add an electron which is spin 1/2, but it's in a big magnetic field, so there's only the spin-up state available. Okay, again, entropy of 0. There's a degeneracy of 1, entropy of 0. So you have 0 entropy with no electrons, 0 entropy with 1 electron. So entropy change is 0. In that case, you have, again, this is the sensor conductance as a function of gate voltage. The blue line is cold, the red line is hot. You can see the transition broaden because the Fermi sea is getting hotter, broader. But that's all that you see. The midpoint doesn't change. On the other hand, if there is an entropy change, then it not only broadens, but it shifts. Okay? So this is the signature of finite entropy. Now, in reality, these shifts are tiny. And so it's very hard to see, to take a curve, let's say cold, and take another curve warm, and look at the difference between those two curves. Experimentally, it just doesn't work. So instead, we take a standard approach for experiment, and that is we just switch quickly between hot and cold, back and forth, and we do a lock-in measurement to figure out the difference between, to watch the difference between these. Okay, and so let me show you what the difference between those two curves look like. In this case, here the blue is above the red, here the blue is below the red, and so the difference looks anti-symmetric, and you can see that it's exactly anti-symmetric. In other words, if you flip around this axis and this axis, you get the same thing again. If there is both a broadening and a shift, it's not anti-symmetric anymore, but now asymmetric. All right, so the positive lobe here is much larger than the negative lobe. And so the signature of this finite entropy change is going to be a line shape as we switch back and forth between hot and cold and look at the difference in the sensor conductance, a line shape that looks like this, asymmetric. Okay, so now let me show you the full experimental layout. Here we have, you've seen most parts of this before. Here we have the region in the middle. We can heat it with a current going through here, or actually, sorry, going through this injector. As we oscillate the temperature here by oscillating this heater current, then we watch for the shift in G-sense. So that was the sensor conductance, and this, we can tee it off and put it in a lock-in to measure the change in the sensor conductance. As I said before, this is all done with a gallium arsenide 2D electron gas, done at low temperatures in a dilution fridge. So we find that it doesn't vary up to a few hundred hertz where our wiring starts to stop being reliable. So I think we typically work at about maybe 50 hertz for I heat, which the heating happens at double the frequency, so it's about 100 hertz. But we've played with that frequency, and it's really not affected by anything until our wiring starts to crap out.
Just wondering what kind of noise is smaller at 50 hertz than it is to make it useful to the one. What's the one source that makes this work?
There's all kinds of 1/f noise that are still active below 50 hertz in our amplifiers, even in the device. Especially in the device, actually. There's all kinds of sort of dopants around that can charge or discharge, and those happen on second time scales. So, yeah. Yeah. Exactly. So the thermal time constants are really short because all we're doing is heating, you know, this region of maybe just 1,000 electrons or 100,000 electrons or something. We're not heating the crystal. We're not heating anything except these 100,000-ish electrons. Sorry? Actually, the most effective thermal conductivity is out to the leads at these temperatures because the electron-photon coupling is so weak. It's uniform, not across this whole region, but all we care about is the temperature here. If we cared about exactly what the temperature was, which sometimes we do, we would have to calibrate it, which we do. But usually we don't care for reasons I'll show you in a moment. Okay, and so again, the approach is oscillate the temperature and watch the oscillations in this sensor conductance. All right, and again, we're looking for this asymmetric line shape as a signature of entropy. And that's exactly what you see. Okay, so here you sweep across the n equals 0 to n equals 1 electron transition. You look at, now, not the sensor itself, which has like a step function, but you look at the changes in that sensor conductance as your oscillating temperature. And it's asymmetric in this way that you should see if the entropy change between 0 and 1 electrons is not 0. Okay, and now I'm just going to flash up the equation that you fit to. It turns out that because the broadening is affected, the broadening is temperature dependent. In fact, is set by temperature. If you go through the full calculation of what this line shape would look like, the asymmetry by itself, without any regard to the magnitude of the various other energies in the problem, conductances, it's the asymmetry by itself that tells you the entropy in units of Boltzmann constant. Okay, and so this, I'm going to show you in a few slides that we actually measure entropy in units of Boltzmann constant to within a few percent. If I then want to go and extract, more or less exactly how much this entropy is in other SI units, then I have to know these other numbers in the problem. And these I can figure out to within, 10 or 20%. This was related to the question of is the temperature uniform? I can figure out the temperature at that location of the reservoir to maybe 10 or 20%. And so if I care, for example, if I need to know this, then I can figure that out. Yeah? That's a great point. I fit to the curve instead of integrating. So I think integrating, you would then, if you want to go back and have this sort of scale-free measurement, you'd have to then divide by the amplitude or something like that. So it turns out that the asymmetry is a more accurate measure than the magnitude itself. So here's the line fit. Here's the number that you get out, 0.71, which may seem, yeah? Hysteresis? You mean the gate voltage? We don't see any hysteresis. As long as we sweep slow enough that there isn't a lock-in time constant. I should say the hysteresis we see is less than any other noise in the problem. Okay, so this number 0.71 may not mean anything to you, except if you ask about what is the degeneracy change between 0 electrons, that's degeneracy of 1 electron, that's degeneracy of 2, then the entropy here is log 2, which is very close to 0.71. And so the best fit of this, you have to maybe combine a few data sets together, do some averaging, but you can really get this number to within just a few percent accuracy. Okay, it's independent of delta t, as it should be, since I argued that all these numbers sort of divide themselves out. We don't need to know what delta t is. Here is the experimentally, input heat as a current. This we can measure very accurately, but this delta t we have to guess, or we have to measure it very roughly, let's say. But it doesn't really matter. We still get this on log 2 with very high degree of accuracy. Okay. Why did this work? We could oscillate the temperature fairly quickly. That reduced 1 over F noise. We could do charge sensing without disturbing the system. We had a thermally broadened transition that was crucial. And also we could keep the temperature changes less than other excitations in the system. What was not required, we didn't need to know exactly what the temperature change was, or the temperature itself, or other energy scales in the problem. Okay, so now I'm just going to flash a few sort of follow-on checks that we did to confirm that this was actually entropy or degeneracy. Of course, people by now are very good at controlling these 1 and 2 and 3 electron spin states in dots. And so this is sort of the more classic picture you would see of one of these 1 electron quantum dots. This is a Coulomb blockade diamond. It's a conductance plot, not entropy. Just to show you a more typical characterization. And here you can see, as a function of in-plane magnetic field, actually you can't see, but if you follow the dotted lines, maybe you can trust me, This ground state splits as a function of magnetic field, and so this is showing you the splitting of that spin degeneracy. We can watch what that does to the entropy. So this is in plane magnetic field. At zero magnetic field, the degeneracy is 2. So you have the log 2 entropy. As you go to G mu B greater than KT, the degeneracy goes back to 1. So now there's no entropy change. And so that's why the entropy falls off from log 2 to 0 as a function of in-plane field. This is what the data looks like. It goes from asymmetric to symmetric as you go from entropy change to none. You can fit this, of course, to the Gibbs entropy that you expect for a two-state system with some energy difference between the states. And you get what you expect. You can extract a G factor from these. We can look at the 1 to 2 electron transition. So now this is going from a state with 1 electron that has a varying entropy to a 2 electron state which has a very different entropy. The singlet state has 0 entropy, but then when you get a singlet-triplet transition, you bring entropy back. Okay, and so that's what you see here as a function of in-plane magnetic field. We start at 0 field with minus log 2. That's the entropy change between 1 electron, which has entropy, to 2 electrons, which has no entropy. Okay, so we drop in entropy. That's why we have negative. And then we go back. Here we have a singlet-triplet crossing. And again, the entropy increases then. You can fit it to the line shapes that it should have. There's a detailed balance version of this same story. And because of the time, I think I'm going to skip over it. It gives you exactly the same result, as of course it has to. But it's a way of seeing the same physics in the language that people maybe are more used to for quantum dots. They're not so used to thinking about thermodynamics in the thermodynamic limit. So I'm happy to go over this with any of you that are interested later. Okay, so we have a new technique for measuring entropy down to Boltzmann constant. The accuracy is very high, within about 5%. The data I've showed you confirmed, physics that surprises no one. We know the entropy of a single spin is log 2. But this level of accuracy shows that this is an effective, or can be an effective technique for looking at much more exotic systems where the entropy is not so simple. So I just want to, in the last few minutes, flash a few examples of what those more exciting systems might be, some examples, and where we're going now. So one is Kondo effect. So I'm sure many of you have heard of Kondo effect. The idea is that if you start with a localized state that has a spin 1/2, it has this degeneracy. If you now couple it to a reservoir of spins at very low temperature, you create this sort of global singlet state between the localized state and the reservoir spins. Its entropy disappears as t goes to 0, or the coupling increases. So this is maybe interesting, at least a few decades ago, because it shows you entropy changing due to interactions in your system, but it ends up that what you start with and end up with after this single channel Kondo effect turns on are all sort of boring states. They're all Fermi-liquid states. However, if you couple this single spin to 2 independent reservoirs that cannot talk to each other, then you overscreen this spin, you end up with a non-Fermi-liquid state that is entangled between the single spin and the spins of the 2 reservoirs, which are themselves entangled with each other. You end up with effectively half of the Majorana fermion, or 1 Majorana fermion, half of the pair in this, as this spin 1/2, and its entropy drops to 1/2 of kb log 2. Not something that you could get with a fermion or a boson. And so measuring this half log 2 entropy is something that's been predicted in many papers, but it's never been seen either for single particles or many particles for these entangled states. I can flash you some data basically showing that we're trying this, but we don't have a good result yet. So I think that's a waste of time for now. If you're interested in how we're doing it, I would love to talk to you about it. One more example I want to show you, though, is this area of Majorana devices for topological quantum computing that is now one of the hot topics in the community. The classic approach for this, for generating Majorana fermions and then detecting them, you generate them often in some structure with strong spin-orbit interaction, coupled to a superconductor. You turn on a large magnetic field, and at some point, this topological phase transition forms. The signature that almost everybody looks at for now is this conductance peak that moves to zero bias and sticks there. And if people see a zero bias peak that sticks to zero, they say we found a Majorana fermion, more or less. And if they don't, they're unhappy. I think what the world is really looking for now is other signatures that give more direct evidence for this Majorana behavior. There's been some beautiful work from Maryland in this area from Shankar Dasarma's group. These are two examples of pictures that show you a Majorana fermion state, this peak sticking to zero. This is sort of what could fool you into being a Majorana fermion state if you couldn't resolve these two levels. You can see that these two look somewhat similar to each other, and so using this feature to distinguish them is dangerous. But Andreev bound states, that's this one, the guy that's maybe fooling us, has an entropy of kb log 2. The Majorana state has an entropy of half kb log 2. And so if we can, notice that these are different by 50%. If we can read this with an accuracy of 5%, then it should be quite straightforward to tell whether we're looking at an Andreev bound state or a Majorana fermion. So these are just two examples. I'm sure there are many more where you engineer in your cryostat or in a theory proposal some exotic new particle. One of the important ingredients to characterize that particle is its entropy, and now I hope I've shown you that we have a way to measure that. So yeah, this is, we can look again at 5 hows, but for now, let me just conclude. I've shown you we have a way of doing a thermodynamic measurement on just a few particles, and I've shown you all the way that that's can be exciting. So thank you.